Okay, welcome. Let's get started. So today we're picking up where we left off last week. So remember last week we were talking about other ways to exploit parallelism within the processor, whether it be using VLIW to get ILP from static scheduling, whether it be using vector to get DLP, or we also saw on Friday another way to exploit TLP by multithreading, that is use multiple threads in the same core. So we're going one step farther and talking about how do we do TLP with multiple cores. So remember, here's our rough taxonomy of types of parallelism. And today we're talking about another form of TLP. In particular, talking about how we're going to use that for using more cores to increase throughput. So the motivation of the course is that you want to get more instructions done in your processor. And fortunately, your workload has multiple threads, in which case you want to use multiple cores to run multiple threads. What might be the issue with that? Well, if you start running, if you simply have multiple cores and they talk to the same memory, this will work fine, right? Because when they perform a load in the store, as long as it's shared same memory, everybody's happy. But as we saw a month ago, usually processors shouldn't talk directly to memory. That's too slow. So we're going to want to put a cache in between. And that's where we start getting ourselves potentially into trouble. So if we put in a cache for each processor, and then they talk to memory, now we potentially are vulnerable, right? Because the issue is, what happens if these two processors both try to read the same address? In the case on this side, that's fine. They can, so I can make this more explicit. Right? You can say you want to do load x, right? Or load x, right? So from the same memory, they're going to get the same value. Great. With caches, now we get in trouble, right? Because now x could be in these caches. And now if one of them wants to keep going, and let's say, for example, change the value of x. So now x is a new value. This processor, core 1, is going to see the new value of x. Core 0 will not. Right? And so what happened here is, with these multiple caches, we were replicating contents of memory, and we allowed them to become incoherent. That is, the same address could be perceived to have multiple values, and so that's wrong. And so how are we going to fix that is kind of the challenge for today's lecture. So the way to think of this is, when we're working on a system where we have main memory, like we're used to, and we're going to have multiple cores, we're going to have caches, and there's actually more things in the system, right? We're also going to want to talk to things like the disk or the network. For now, we're going to forget the I/O. But mostly we want to have multiple cores talking in memory, and we want them to have caches to go fast, but how do we keep these caches coherent? So as the slide is kind of alluding to, we do something called snooping. So I'm going to explain what that means in the next few minutes. But in this particular way we're doing it, the key enabling hardware is actually this bus. So normally buses are not great in architecture because you have many readers, many writers, there's not a lot of bandwidth. But in this case, because everyone's trying to talk over the same shared medium, it's actually a feature. So to kind of go into more detail about a bus, usually it's a collection of wires where you have multiple things that want to be both a reader or a writer. And so I apologize for the dated terminology here of master and slave. It's unfortunate what the hardware community is still doing. It's just now starting to change. But the notion being that when someone intends to write, they need to somehow arbitrate with the other potential writers to get permission to write, and then they write. And so the point of this bus in this example is that there's only a single writer and multiple readers. At any given time, somehow the writers arbitrate and pick which writer gets the right to write, they get to write, and then everyone else listens. So to solve this coherence problem, as I kind of said a few minutes ago, something called a Snoopy cache or a snooping cache. And the idea is, when we got in trouble over here, The problem was we made a change here, but a change wasn't made in memory or in another copy in the other cache. So the idea being, well, instead of allowing people to kind of do what they want, if instead we put things on a shared bus between them, we can see these operations going by. So we can see the other processor writing to that cache line, and we know it's going to cause problems. Right? And so in order to do this, we're actually going to need to add more ports within our cache. Right? Before, only the processor needs to be able to read the tags to see if anything's there. Now the snooping agent also needs to be able to read the tags to see what things are inside the cache and which things are being updated by watching them go by in the bus, and if anything matches, potentially change something. So what kind of things would you change? Well, there's really only a couple of cases we need to worry about. If we have the data already in our cache and our coherence protocols are doing its job correctly, things are pretty good. So we have misses, we've got to be careful. So on a write miss, for example, if I want to write data, if someone else has a copy of that data in their cache, they're the ones who are at risk of getting the wrong result. Right? This is an example we just talked about here, right, where both of them did a load, so they had the value inside their cache. This is the one that wants to do a store. This new value, better make sure there's not someone else thinks I have X over here. So for a write miss, if you want to do write, you need to make sure other cores don't have that data anymore. Otherwise, or it's referred to as invalidation or invalidating it. Otherwise, they're going to be in trouble. Now, on a read miss, there's a few different ways to handle this. But at the end of the day, you're going to need to get a copy of that data. And we'll see that sometimes that data will be dirty in another cache, or sometimes it'll be in memory. But either way, you need to get the data from them. So let's put this all together into an example coherence protocol. So basically, about the simplest commonly used protocol is something called an MSI protocol. These letters are referring to the legal states a cache line can be in. So for every cache line in the cache, you add these extra bits for the coherence protocol to track what state is it in. And so in this case, because there's only 3 states, we of course can have 2 extra bits for those states. So what are these 3 states? Modified, shared, and invalid. So, and this is of course from the point of view of the cache attached to processor 1. So let's go through them, right? So invalid means, as the kind of implies, this cache line is not being used or is not in my cache, right? So it's not present. We need a little mark that to keep track of things. So invalid means it's not present or not being used in this cache. Fine, it's kind of like a base point. Now if the data is in my cache, that means it can be either an M or S, I mean modified or shared. What do those two mean? Well, modified means the data I have is different than memory. It's somehow dirty, so to speak. In addition, as I just told you in a previous slide about the fact that when you want to write data, you need to make sure everyone else invalidates. If you have a modified cache line in the protocol I'm teaching you so far, you're only one with it. Now, if it's shared in a shared state, multiple caches can have this cache line, but it's read-only. It's not been modified. There's been no changes to it. So let's kind of fill in this finite state machine here. So first, let's say you do a read miss. So then you're going to need to read the data from memory. And because the data has not been modified, you can describe it as, is in the shared state. Now, if other caches also wanted to read, it would stay in the shared state, right? So they could, any processor can also request that data and then go into the shared state. Now, like I said, if somebody wants to write, then we got to start invalidating, right? We'll make sure none of these other copies get the wrong results. So if another processor wants to write, it needs to make sure every other processor invalidates their data, right? So in this case, P1 had the data in the shared state. Some other processor wanted to write to it. And the other processor requested the intent to write. And so processor 1 invalidated itself. It ejected the data and put the cache state in I. Now, if P1 itself wants to write the data, then it expresses its intent to write. And of course, expresses this over that bus. And then it can go to the M state. So now it's in the M state, the modified state. It can do all the reads or writes it wants. However, while it's in the M state, if another processor wants to write it, they're going to basically yank the cache line away from processor 1, and it's going to have to go to the invalidate state. Now, there's a few other conditions that can happen. Perhaps you're in the M state, and another processor wants to read that data. Well, you're going to need to copy the data not only to the core that's requesting it, but also to memory. And we put it in the shared state. In the shared state, remember, that's saying that the data inside the cache and memory are the same. And that's kind of another way to go about it. And let's say from the beginning, maybe you didn't start in the shared state. Maybe you started and you wanted to do a write miss originally. Well, once you pull the data in, you're going to need to go to the M state. As we've seen, everyone else needs to go to the I state. So I'm going to pause here for questions. OK, we'll keep going forward. Some of you may have seen some of these coherence protocols before. But I'll keep going, and perhaps there'll be some of you you've not seen before. OK, so to be a little more concrete, we're going to do an example. So we have two different cores, or two different processors, P1, P2. They're reading and writing the exact same cache line. So we're going to have these states for each cache line inside a cache. Right now, we're simplifying our problem to just talking about a single cache line. OK, so if processor 1 wants to do a read, well, it's the first time I've accessed this cache line, so it's going to have a read miss. OK, great. And then now it wants to do a write. Well, it uses that bus to broadcast its intent to write, and then gets into the M state, the modified state. And now in an M state, I can do all the reads and writes I want. Great. Now if P2 wants to do a read, what's going to happen? Well, it's going to be initially coming into this shared state, because of course it wants the data. However, P1 cannot stay in the M state, right? If it's going to allow someone else to read it, it has to downgrade itself back to S. And in order to do that, it needs to both write the data back to memory, and as well as allowing P2 to do a read. And what's great is because we have this bus that's sharing everything, when it's broadcasting the memory, the data from that cache line to do the write back to memory, it's also the same time P2 can read it. So they both can kind of read it at the same time. Great, so that's now how we did P2 doing a read. So now we have processor 1 in the shared state, processor 2 in the shared state. Now all of a sudden processor 2 wants to do a write. So what's going to happen? Well, it's going to express its intent to write, which is going to cause processor 1 has to invalidate itself, right? Because it can't have a copy, because the other one is going to go into modified. And processor 2 is going to go from shared to modified, right? Because we want to modify it. We want to go to M in order to write, right? So you might see some kind of trends occurring, right? For example, one rule is that you can't write a cache line unless you're in the M state. So if you want to write a cache line, you need to get to the M state, and then once you're there is one time you're allowed to modify it. OK, so then it wanted to modify. So now we have processor 2 into modified, processor 1 invalid. Now that we're modified, processor 2 can do all the reads and writes it likes. But now let's say P1 reads. Oh no, OK, so now we're going to have to go through this all over again, right? So OK, so P1 wants to read. This is the exact same sequence again, just inverted, right? So now it's going to have a read miss, and so P1 is going to go into shared state. And P2 is going to have to write the data back. And itself is going to downgrade from M to S, right? It's going to have to go from modified to shared, because now it no longer has a uniquely dirty copy of the data. It has a shared read-only copy. And so now they're both in the S state again. And then, well, if P1 writes, we know what happens. Well, then we have to do the intent to write. It's going to invalidate the copy in P2. And it's going to go to M again. And so you see in this example where we have these two processors reading and writing the same cache line, it actually generates quite a bit of traffic on this coherence protocol, where we know, and you're going back and forth between the M state, the S state, even the I state in some cases. And so this repeats on and on. In this example, questions?
So the I state is the same I state as if the cache line wasn't there.
Correct.
So it's overloading the valid bit.
Correct, yeah. So depending on how you actually encode this inside a cache, you may actually be able to reuse the existing valid bit and then add only a single letter bit, for example. Yes, go ahead.
So when P1 writes in the second line there, and then P2 wants to read it, does it actually go from, it must be in an invalid state at that point. Does it then go to an attempt in a shared state?
Okay, so let's break this down. So you said when P1 does the first write,
Yeah.
okay, so at that point, we didn't show it, but P2 was in the I state.
Okay. So really what happens when P2 reads is it goes from I to attempt to go to S.
Yeah.
It can't do it, so P1 then goes to S, and then it can read it.
Yeah, so the reason why it's not necessarily shown that way, perhaps, is that a given piece of hardware in the cache, depending on the contents of the tag, represent many different cache lines, right? And so if it's not present in the cache, as was previously asked, it's basically think of it as I. And so let's say you can think of it as I, but the fact is it's not even in the cache at all. And so, yeah, I think we're kind of on the same page here, where it's like data is not in the cache is definitely I. And how you choose to think about it in terms of these finite state machine state bits is kind of your interpretation of how you interpret valid and not valid. But yes, not being in the cache or invalid are equivalent.
Okay, so the bottom line is that whenever it wants to read, it has to read it from the shared state, unless it's the sole owner of it.
Yes, yes. For this MSI protocol, yes. Yeah, so perhaps to give a bit more context. So there's a whole slew of these protocols, and they get a lot more complicated. Not only are there more states, but they often have more transit states, right? So we're not really showing the transitory states. We're kind of using the atomicity of the bus kind of as a nice convenience. But there's a lot of complexity can come into these. And so, yes, in the MSI protocol, and this, basically the simplest thing you can imagine, you can only, if you're in S, is the only time you can read, unless you're in the M state. So you can read in M or S. You can only write in M. Only one processor can be in M for a given cache line at a time. Many processors can be in the S state at a given time. So this is the MSI protocol. Technically, you can imagine an even simpler protocol, which is basically just MI, where either you have the only copy of data in your cache or it's invalid. That's theoretically possible. That would really cut into the utility of your multi-core system, because that would basically mean that these two cores couldn't touch the same piece of data, even if they're only reading it. If they're reading and writing the same data, clearly there's implicit and necessary track between the two, and you have to kind of required to do it. But if you only wanted to read the same data, which may happen not beyond your program, maybe the OS, for example, wants to read the same page shell register or something, that would be really problematic. So in theory, you could actually strip this down to an MI, but that would not be too useful. Great, more questions?
It seems like there's a practical limit to how many processors you could connect to a bus. And at some point, it's going to have to get more of a ring-oriented approach.
Yes, absolutely. So that's what we're talking about later in the lecture today. It's called directory-based coherence, where in snooping with just shared bus, where everyone kind of can see all the things going on. And as you're absolutely right, if you're constantly broadcasting, that's got to have some sort of inherent limit. A directory structure we'll use to be more specific about who we're talking to. And that will help reduce the traffic and scale to higher core counts. In spite of that, snooping is still used in some places in some ways in contemporary cores. Modern server cores tend to mix a bit of both. It's not quite purely snooping, not quite purely directory. There's a little bit in one place, a little bit in another place. But for this course, most of the coherence efforts will be on snooping. And we'll talk about directory too. But it's kind of the difference of what are these states of the cache lines. And the coherence protocol is one thing. And then what's the mechanism used to communicate and implement the protocol, which is snooping or directory. So right now we're talking about snooping, which is this shared bus. We'll talk about directories later. But if you really want to, you can often easily port over different protocols to a different implementation substrate. Good. OK. So yeah, this thing's repeating a few more times, but we got the gist of it. So what's happening? Well, this is our basic MSI state diagram. And so some of these things we've already just talked about, right? So if a line is in the M state, then nobody else can have a copy of it. And we can't. And the good thing is it accomplishes our goal, and that is we can't have multiple different copies present in caches, right? We're going to knock things out before we're allowed there to be different copies that are not the same. So people refer to this as coherency, right? Where is the same address perceived to be the same value? And that's coherence. OK. So one of the issues is, as you might notice, there's a lot of things end up in this I state. And so what's wrong with the I state? Well, if you are in other states and keep going back to this I state, that's kind of forcing you to reload data from memory. And on the plus side, by reloading from memory, you're getting coherent copy. On the downside, it's more traffic, more reading, et cetera. So as I said, there's a few additional extensions to these protocols. The next one up, people often talk about, is referred to as a messy protocol. So it's the same as the MSI protocol, but now we've added an E state for exclusive but unmodified. So what does that mean? So if something's an E state, only one core can have that cache line in the E state. The copy it has is the exact same as the one in memory. So it's not been changed. It's clean, it's not dirty, however you want to describe that. But they're the only one that has it. So this can speed up some cases, right? So from before, for example, if you do a read miss, you're going to go into shared, and anybody can read it. And if you want to write, we'll have to go into modified. And once you're in modified, you can read and write it. But here's where it gets different. With the E state, if you're the only person asking for this cache line, rather than going to that shared state, you can go into the E state. So now, why is that better? Well, you can stay in E state, and you can keep doing reads to your heart's content inside the E state. But now when it comes time to write, you can go straight to the M state. Right? And so why is that better? Well, normally, if you want to do a write, you have to kind of do this whole broadcast thing where you have to tell everybody I intend to write and broadcast it out, and everyone else has to invalidate. If you're in the E state, you don't need to tell anybody because you're already in E state. You already have exclusive control of this cache line. You can go straight to M. And it's actually a very common pattern in many programs, right? You can imagine where your code is going to want to load a value from memory, look at it, think about it, and then modify it, right? So it can typically read before it writes. And so if you're the only one who's reading it, you basically can get the exclusive access right away. And then when you want to upgrade your access to writes, you can do that without having to broadcast. Now, if you're in that E state and someone else wants to read the data, well, now they'll have a copy, and you won't be exclusive anymore. So now it's going to be sent back over. And so now the two of you are going to be in a shared state. And of course, once you're in a shared state, if you want to do write, or anyone wants to do write, you all need to be invalidated, and that person who wants to write has to go to the M state, right? So, great. So then someone else wants to write, you all are invalidated. If you're the one who wants to write, then of course you can go to the M state. So likewise, if you're in E state and someone else wants to write, you also need to be invalidated, just like before. So it's mostly the same, just now we have this new state where if nobody else has this line, even on a read, I can go into this E state, which allows me to go to M state faster when I want to do write later on. But maybe I won't do write later on, and I can go from E to S without any hassle. Question?
Just to confirm, there's a missing arrow at the moment from July, right?
Oh, sorry, that's another build. Yes, I mean, yeah. I mean, actually, I'm sorry, I didn't build the whole thing. There's actually 2 more builds left, apparently. Yeah, so if you're in the M state and someone else wants to read, if you write the data back to memory, you can go to the shared state, because now you have the same value as the one in memory. That one makes sense. And now there's one more line. Now if you're in the M and someone else wants to write that data, you're going to need to be invalidated. And before you invalidate yourself, you're also going to need to write your data back. So yeah, so now this is the full table. That was sorry, the previous one was not full. Another question?
Is there any kind of forwarding between these states, or once you go invalid and then you reread it, you have to get it from memory? Meaning you go from explicit to shared and then actually forward the value?
Yeah, great question. So the answer is yes, that's possible. It depends on which protocol you're doing. So we're kind of doing a bottom-up approach with these very basic protocols where when in doubt, we're kind of reading and writing things to and from memory, which, as you're absolutely correct, that if the data is already available on chip, that seems really slow. So people refer to those kinds of optimizations as, forwarding or update protocols, where you can send data more directly. Later in the lecture, I'm going to cover an additional state called O, or for owned, and that will handle that case. But it's not the only one that handles that case. I'm not talking about in this course. Some people refer to it as the F state, or the forward state. But yes, to answer your question, more sophisticated protocols can definitely send data between each other on chip rather than going to memory. To give you a sense of the kind of what we're talking about, so here we're talking about maybe 3 or 4 states. If you actually were to pull up the details of the design team for let's say the Power 8, which is the big IBM server processors, coherence protocol, that one I forget numbers for. The last time I heard numbers for was the Power 7, which was 14 states. And so the reason why the number gets so high is a lot of transitory states, because these things can't happen instantly. So it's like, okay, well, I'm going from here to here, and I'm on the way, and I'm waiting for everything to happen before I make the full transition. And so once things start taking multiple cycles and multiple steps, and you may have less guarantees about the broadcastness of your network medium, it gets much harder to be correct. So one of the biggest concerns people implement these protocols in practice, and are getting more complicated protocols, is how to make sure I don't deadlock. How to make sure I'm not in some combination of finite state machines that are something that doesn't happen. And so they spend quite a bit of resources to try to improve their coherence protocols that are deadlock free. It's actually one of the few cases in processor design formal verification works really well, but it still might take a supercomputer months to do it. But yes, answer your question from originally, yes, you can forward on chips sometimes. Okay. So the question might be, well, where do you put this coherence information? Right? If you do this on every single access, that might be a lot of overhead. So, for example, if you have a 2-level cache hierarchy, you actually only put it on the last level before you go share it. So for these private caches, you can have the L1 not worry about coherence, and have the L2 for each core worry about coherence, right? And this is easily done if you have an inclusive cache, right? If it's inclusive, that means everything in the L1 is present in the L2. And more importantly, if it's not in the L2, it's not in the L1. So thus, as long as the L2 does all the right operations for maintaining coherence, and when it needs to update the L1 as well, you're OK. So I realize this is a little bit different from before. Before we had our single processor view, some combination of misses made trigger replacements in the L1 and L2, but that was kind of, going this way down. Now it's the other way around. Now the snooping thing may say, oh no, I need to invalidate this cache link, and someone else wants to write it, so now I need to yank it out of the L1. So now it can come the other direction. But what's great about this is snooping takes a considerable amount of bandwidth, right? Because we're watching a transaction go by, as well as the snooper needs to read the tags of the L2 to see are these things present or not. What's nice about this design is that we can use the L2 resources for snooping and all of both the bandwidth and the tag checks, but that now unburdens the L1. The L1 can now be very fast, doesn't need to really know about coherence. It can go faster to the CPU. It does need to allow itself to be interrupted, hopefully rarely, when the L2 tells it it needs to invalidate a cache line. So this is kind of a common design. As you'll see that typically we try to push coherence farther away when possible. If these caches are doing their job, of course, the bandwidth here will be higher than the bandwidth here, than the higher than the bandwidth here, right? If things should be present in the L1, hopefully. If they're not present in the L1, you hope they're present in the L2. And if they're present in neither cache, well, that's going to happen some of the time. Hopefully that's the rarest situation, right? So this is good, right? Because that means we're using these caches kind of like filters, right? We're filtering out most of our requests. And only those requests that miss in the L1 and the L2 that need to go to memory are also going to be involved in those with the snooping for other caches to make sure we're not getting an incoherent view. So to kind of see that play out, what happens? Well, here we have a really simple example where processor, we have one CPU that had data, we read address A, it got into the modified state, and so this data is now different than the one in memory. And so without, intelligent coherence protocol implementation, processor 2 is going to go request, hey, I need address A, and it's going to ask for memory for that data, and memory is going to say, oh, I have address A, yes, here's 100, right? But we don't want to do that, right? Because that's the wrong value. And so this is where the coherence protocol is going to need to intervene and say, okay, wait, you want to read address A, I have a modified copy, thus I need to go to shared and write this back and intervene to tell you the right data. So for example, in this case, we could definitely do what was described just a few minutes ago of forwarding data on that memory bus. We're in the process of writing back this value as part of the invalidation, or sharing it. It both gets sent to memory and to processor 2 at the same time. We can forward that data. But the key point is that, with snooping, you can't just, take the data and forget about it. You have to kind of be a constant participant in the coherence protocol to make sure that, someone else wants the data, they're going to get the right data. So I was going to run a couple examples to show this might play out. So let's see if we can pull this up. OK, so here we have 3 different cores, each accessing the same address. I'm going to try and go back in the slides to put up the coherence diagram. How can I do that? Great. I can go here. Great. OK, so what's going to happen? Well, let's say it's starting off where everybody is invalid originally. So if everybody's invalid originally and core 0 does a load, where's it going to go? Sure, it's going to go to L1 cache. What coherence state would it go into?
Shared.
Yeah, so I heard both. Shared would be correct for MSI, but since we have this E state, and because no one else has it, we can go to the E state. But shared is not wrong. It's just E would be better in this case. OK, so it's going to go into the E state. Great. Now, this next, so that means it's in the E state. It has, this thing loaded in there. So it's in the L1 and it's in here. Now, core 1, requests that data and then wants to do a store. So it's going to send out on the bus. I'm going to do a store. And so as the result, what's going to happen? We're going to have to send some messages, right? So what's going to happen? We're going to send a message of, write and miss. It's going to have a write and miss. Then it's going to say, intent to write 100, right? And then what's going to happen coherence-wise? Yeah, so this one has to give up the data, right? Because it sees this on the bus. So it saw that, right, intent to write. So it's going to delete this. And it's going to go to I. And this one's going to go to M. So now we have potentially, we can say potentially dirty data, right? So now, for example, if core 2 wants to read it, what's it going to do? It says it wants to read 100. This one's already I, so it's not going to matter. This one's going to see that request. And well, since someone else is reading it, it's going to go from M to S, and it's going to put that data on the bus, right? So that data is going to come over here. So it's going to have this, and this is going to go into shared. But it's also going to go back to memory, right? Because it's going to broadcast it out because it had to do the write back. Question?
So you go from I directly to M without having to bypass through S? Because you got to kick out whatever was at M or E.
Oh, so you're saying, could I go from, so say that again? Can I go from I to what?
You went directly from I, assuming like your initial state for L1 cache was I.
Yes.
You went from I to M.
Correct.
Without like waiting for it to have been free, if you will.
Yeah, so depending on the semantics of your protocol, because it's a shared bus, you kind of can trust everybody else can see what you're doing. And so you're right. You normally need to wait for acknowledgement that nobody else has that in the M state.
Read intent to write. You can assume on like in the clock cycle, if you will, on that one, it's also moved from M to S or from E to S or from M to I or E to I.
Yeah, depending on what's the right coherent transition, right? It's going to go from there. So you can go from I to M. You're right if someone else has the data in the M state. You want to make sure it gets written back to memory, and you read that before you modify it. So this is what I was referring to earlier about these transitory states that are happening in practice when you implement these protocols. They make this complex in a hurry. So for these courses, we don't usually talk about those. So yeah, so in that case, we really can say it's going to go from I to M. And you're right. If someone else has an M, they need to write it back, and I need to read that first. But from the point of view of the coherence protocol transitions, we're going to say it goes from I to M. Great.
I'm a little confused on that. So if I'm going to write a memory address, I don't need to read it first. But I do need the S transition to occur on the other caches.
So there's one detail which I perhaps omitted. It might make that more clear. Usually you do coherence protocol at the granularity of a cache line. So this is very analogous to the issue we had in the caches a month ago. We're talking about what do you do on a write miss? Do you do a write allocate or a write no allocate, right? Because if I'm writing data, why do I need to read the cache line in? Well, if I'm writing one word in the cache line 16 words, what's that data going to be, right? So if you have a write through cache, this doesn't matter because if it's non-new cache, you can just put it straight into memory. But if you have a write back cache, you have a write allocate cache and the write back cache, you have to, even on a write miss, you bring the data in because you're only updating part of the cache line.
Oh, because
so
I've become authoritative for that line.
Yeah, so in the case of this, where if we're doing this in the granularity of cache lines, yes, even though I'm doing a write, now that I'm as you say, the authority for that cache line, I need to also provide the other words for it there. Later in the lecture today, I'll be talking about all sorts of issues that can happen when you have multiple words sharing the same cache line for the sake of coherence. It makes something very complicated. So if we want to roll back what we talked about 5 minutes ago, hypothetically, if I did coherence to the granularity of a word and I was doing a write to a word, technically I would not need to do read for the M state. The way to think of this is kind of like we're layering this coherence protocol on top of whatever your cache is in the first place. So most caches we're dealing for this course are going to be write back and write allocate on a miss. And so given that, if you want to do a write, you're going to need to bring the data in. And then these protocols kind of telling you, well, how do I make sure I have the permission to write? Do I need to wait for someone else to invalidate? Do I need to discard my copy because someone else is going to write to it, et cetera? Oops, I actually probably should leave it on this slide, and then I should do one more quick example. Let's do another one. So zoom out a little bit. So what do we have? Well, we have just 2 cores this time. And this one perhaps is way more clear. We're going to be much more explicit about what happens. So actually, I'll do even one better. I'll very clearly show by color which one is going to happen to each one, right? So for operation A, which is this load, well, we're starting an invalid. Nobody else has it, so we're going to go into E. And for completeness, we can say core 1's an I. Now for operation B, I need to change to the screen. I want to do another load. That's fine. I can stay there, so I can stay in E. And nothing's going to change for core 1. Now operation C. Now we want to do a load. What are we going to do? We're going to need to get the data. Yes, I should go back a little bit, right? So originally, 100 was copied over. No additional transactions were required for operation B. For operation C, now they want to do a read, so it's going to go into the shared state. It's going to also cause, yeah, I should be more clear, right? So it's going to have, request read to 100 is a transaction going on the bus. And then it's going to come back, get the data back at 100. Now for this one, same thing. We're going to request read 100. And since this L1 cache from core 0 is going to see that request to read, it's going to automatically downgrade itself from E to S. And then for the final one, now I'm going to say intent to write 100. What's going to happen? Well, you're going to send that broadcast out. You're going to eventually get to the M state. They're going to need to see that happening. And they're going to go to the I state. And core 0, because it's in the S state, the copy memory is correct, right? So it doesn't need to write anything back. It just discards it. OK, more questions?
So I'm kind of thinking about this protocol. The core 1 cache, for example, at the beginning, it doesn't know that anyone else has 100 because it's not remembering cache lines that it's not aware of.
Correct.
Because it can't have a memory.
Yeah.
cache. So it's got no information about that. And the decision to go from I to S when it receives, when it goes for its load, it's really dependent on other devices on the bus to tell it, by the way, I had this.
Correct, yeah, that's a level of detail I did not show here where for an MSI protocol, what I showed is correct. But you're right, in order for you to get an E state, you need to know that nobody else has it. So you would send something of the equivalent of intent to read, or just really your read request. And when you get it back, you're going to go to either E or S, right? You're going to one of those two states. Whether or not you go to E or S is determined by if anybody else says, I have that too, right? If someone else says, I have that too, they're going to speak up. They can hear that transaction going by in the bus. They're going to say, oh yeah, no, I have 100. You can't go to E because I have that. If they hear nothing, they can assume that they're the only one.
So does that piggyback on the data transfer, or does it?
Yes, so exactly right. So this is what's nice about snooping with these shared buses. Everyone can kind of see everything that's going on. So the bad news is, as you alluded to earlier, it's not so scalable. But the good news is, it can see things happening, right? So it can see the fact that, yes, core 1 is requesting address 100, or originally it's core 0 requests address 100. And it goes to memory. Memory says, here's data for address 100. Great. And then nobody else responded. So it's OK, no one said anything. I can go to E state. When core 1 asks for address 100, maybe it's better if I draw that right. So that's, I guess, operation C. There's going to be some sort of acknowledgement of I have I don't know if you want to say I have 100, right? And that's what tells core 1 to not go into the E state. Question?
What if there is, if instruction C is not there?
Mm-hmm. Yes, that was the case we talked about a few minutes ago. Yes, it could. Yeah, so it would say, I intend to write this. And so core 0 would, listening on the bus, could see, okay, someone's writing to this. I have it in the shared state, so I can just discard it, right? Now, if I had this in the M state, I needed to write back. I'm going to broadcast out, wait, I'm doing a write back on this. And then the other person needs to listen for that data and pull it in. And depending on what your protocol is forwarding, as I described, if you naively implement this protocol, you can write it back to memory and read it in over here. If it's more intelligent, it'll see that write going back to memory on the bus and pull it in at that point to save another transfer. Good questions. OK, so I think, so we've talked about messy so far. The most common additional state people have is something called own, which is going back to the other thing we were just talking about. So this O state means that you have a copy, and it may be different than what's in memory. And the reason why you would want to do this is now you respond, right? So this is going to be helpful because you can reduce that latency, where if someone else wants to do it, you can just now forward directly from the other cache rather than going to memory. And so you can imagine if you actually have two different caches ping-ponging the same line, this is going to reduce the number of times you need to go to memory. Normally, you have to kind of keep it right back and validating the memory. With this own state, you can now be the one who responds. OK, I think we're maybe ready for a peer instruction question.
Why do you need E if you have O?
Why do we need E if you have O? So O means that you're going to respond to people's requests for the data. It does not mean you have the right to go to the M state without intervention. I believe so. Yes, but everyone else needs to know. So the reason why the E state worked before was if you're in the E state, other cores cannot be in the M state, right? So if you're in E, they can't be in M. And their process of going to M will invalidate that. So whether you're in E or M, other cores can't tell. If you're O, other cores can be in S.
Right, that doesn't matter because if you write to your own cache line.
What's the thing? So if you're in the E state and you write, you go from E to M.
Yeah.
Nobody's in S. They can't be in S. So you can do that silently. If you're in the O state, other caches can be in the S state. So now if you now all of a sudden modify that, they now need to be notified of that change. And so depending on how your protocol implements this is why I didn't show a Mosey diagram, because there's multiple ways to do a Mosey. Depending on how you implement this case, right, either if you go from O to M, and you're going to validate all of them, or you're going to stay in O and broadcast an update. Like, oh, by the way, this shared cache line now has a new value. Here it is. It's kind of like a write service or write back approach to it.
Okay, so it's not that you're not allowed to modify that memory, it's that you're not allowed to move the M state. And
You can move the M state, but you can't do it without talking to everyone else about it.
exactly. Sure.
Yeah. Question?
So if you're in O state, you're saying that the process would try to read, which means that it would go to S state?
So no. So if you're in O, someone else can go to S, and you can send them the data faster than memory can.
So, I mean, the code with O will not change.
No.
That's another question on granularity. So the CPU is sending reads and writes to the L1 cache at the word level. But all of these operations on the data bus are happening at the cache line level.
Yes.
So the states apply to the full line,
Yes.
not just to a word.
Correct. Yeah. So unless told otherwise, you can assume coherence is maintained at a cache line granularity. I mean, in general, all cache operations basically work at a cache line granularity, with the exception of the L1 doing the reads. But like L1, L2 transfers, those are at a cache line. So everything between caches normally is cache line. It's just at that last step inside the processor, you have to cut it down. OK, so let's go into pure instruction. I think we kind of maybe talked about this a little bit indirectly, but maybe we'll be more explicit. So we have a system. We're doing only Messy, not Mosey. Talking about a single cache line, or single cache line address. Looking at all the different possible states across all of the caches, which states are possible. So for example, A is saying, the question is, and make this more clear, which is not valid. So that's implying that 3 out of 4 of these are okay combinations of states, and 1 of these is not okay. So think about that for a second, about which combinations of states is not okay.
Based off what you just said, though, 2 things that are
Yeah, I'm actually right now, and I can see an exact typo. So how about this? Why don't I scan you guys to get credit for attendance, then I'll fix the question. Yeah, you're absolutely right. So a very astute point. As you can see from that question, 2 of those are okay, 2 of them are not okay. So my question of there being a single wrong answer does not really apply. But why don't I scan, and then we'll talk about it.
You didn't say there's only one right answer.
Okay, fair enough. There could be multiple right answers. Normally I try to have there only be one right one. I appreciate the forcefulness. Okay, so let's talk about it. I think we kind of talked a little bit indirectly. So M plus S, is that okay? No, right? Because modified needs to be kind of on its own, right? You're only one allowed to modify it. So if you're modified and they're sharing, in this messy protocol the way I've shown you, not okay. Can you be exclusive and else be invalid? Sure. Yeah, that's fine. Can multiple cores be shared and one is more than valid? Yeah, that's also okay. And then this last one is the one that's also suspicious. You have it exclusively, and yet someone else also has it shared, right? That seems inconsistent, right? That's not okay. So,
But the argument for why it'd be okay in that, like the ES, is yeah, you have exclusively, but the moment you go to write, you go to M. When you go to M, you kick everything out of S. So it's okay under that assumption. Because what you say is exclusive allows you to read and write. The moment you go to write.
no, exclusive allows you to transition to M.
Sorry, yeah, it allows you to transition out.
Yeah, so this is that question from 10 minutes ago about why do we have O if there's E? Yeah. So if you were O and S, that would be okay, right? Because you can send it, when someone else wants to read that data, you can respond faster than memory can, and they all can read it. And if you want to write it, you can tell everybody, hey, I want to write this. They're all going to invalidate, and then you're going to go to M. With the E state, yeah, you can go from E to M without telling anybody because you have it exclusively. So because the semantics of E, you're exclusive since someone else should not be shared. Yeah, so I apologize for making a typo in this question. I'm now trying to wonder what I was thinking last night, which one was supposed to be the wrong one. But that'll be a good catch for everyone else to have this conversation. Okay, so let's keep going. So I think we talked about this a little bit already. Maybe we get more explicit. This issue of doing coherence at the granularity of a cache line when there's multiple words in a cache line, right? And so the result is actually just a few things that happen, right? So imagine you're doing operations on different words inside the same cache line, and they're different words, but it's the same cache line. What can happen, of course, is it's going to trigger coherence actions, even though these two pieces of data are not really related, other than the fact they happen to be located near each other in memory. And so when this happens, it's referred to as false sharing. When you have accesses to different words inside the same cache line, triggering coherence traffic. And this is actually one of the most common issues that holds back programmers trying to write parallel code. You're trying to write high-performance multi-threaded code across multiple cores. False sharing, I would say, is the most common way a programmer hurts the performance because even though they've done a very good job of separating which data goes to which thread, and they aren't interacting, because of the way the data is laid out, even though talking to different words inside the same cache line, so the data is going back and forth between the same cache line. So I have some slides from the textbook that will show how this might play out in a real workload. So if you have a big system, with a lot of processors in it, in the old days we referred to as SMPs, for symmetric multiprocessors, meaning you had a uniform access to memory. But now that we have coherence in there, we now have a fourth C for our caches. Remember earlier when we had our three C's of caches, it was compulsory, capacity, and conflict. Now the fourth one is coherence, right? Where the reason why a data is not in your cache, it could have been in your cache previously, but perhaps it was yanked out by an invalidation or something. So that's what a coherence miss is. And so of these coherence misses, there's two flavors that can be caused based on these issues of doing coherence in the granularity of a cache line, but moving data in the granularity of a single word. So true sharing is when we actually are doing the same word, right? Where if two different cores are trying to read and write the same word, it's going to trigger cache coherence. That's what we want, right? Because it is the same word. We have to keep it coherent. Now, false sharing is the one we want to avoid. That's the case where these two cores are touching different words that happen to be in the same cache line, and thus they're triggering transactions even though we don't want it. Like you can imagine, for example, if I go back a few slides, let's say core 0, let's go around. Okay, let's say core 0 is adding to a counter and core 1 is adding to a counter. And they're different counters, word 0, word 1. They're both going to constantly be invalidating each other and modify and validate, even though they're not the same data, right? So that's false sharing, right? But if they're trying to modify the same counter, that's true sharing, right? So you have to handle that. So if we want to get technical about how do we distinguish these two, it's true sharing if the coherence traffic will still happen if we reduce the granularity of cache coherence down to a single word, right? So basically, false sharing is a byproduct of the fact that our coherence granularity is greater than our access granularity. If that's the case, that can cause false sharing. If those two are the same and there's still coherence traffic, that's true sharing. So to kind of drive this home, we have a little example, right? So we have two addresses that are different words but in the same cache line. And we have two processors, P1, P2. So what's going to happen, right? So first, P1 writes to that address. So it's going to be a miss. And if there was a copy in P2, it's going to be invalidated, right? Because it's going to see that write going through. All right, now, if P2 wants to do a read to the other address, that's going to be a false miss, right? Because X2 is not the same as X1. It's a different address. It's the same cache line. Right? And so P2 doesn't care about X1, right? It only cares about X2. But because they're in the same cache line, it's going to trigger this coherence traffic. So that's a false miss. Now let's say P1 writes to X1 again. That's also going to be a false miss, right? Because it's the same cache line, different word. It's going to be triggering coherence data. And once again, P2 does not really care about X1, right? Just the same as P1 does not care about X2. But these are going to trigger more transactions. Now, so what else happens, right? So initially, we had, mi, then this read puts it into some sort of shared, and this goes to I, then we write, so this goes to m, and here for P2 it goes to I. Now I'm going to read again. Sorry, I want to write again, but I have to. That's interesting. Okay. So what's going to happen here? So now that we're going to do it again, we want to do the same address, but I didn't have permission to do so. And then finally, we can fill this table. So maybe fill the table out. It's more easy to kind of work our way backwards. So if these are two separate cache lines, what would have happened? If these are two separate cache lines, this would have gone to M and just stayed in M, right? Because this one's only writing to X2. This one's writing to X1 only for here. And then it's going to go to X2, right? What's happening over here? This one's also only doing X2. So this would go to S, and then to M, and then, well, it's going to go to S here as it goes over here, right? So the coherence interactions are going to be different because these two are packed into the same cache line.
I think there's a typo in that last line. It should be P2 that you invalidate X2.
Yes. Okay, I agree. Yeah, let me write that one down. Yeah, that's correct. That should be P2. I agree. Okay. Question?
Can you explain time 3 once again?
Okay, so times 3. Okay, so remind ourselves after the time 2. So at time 2, we had a system such that both caches were in the S state, right? And we call this a false miss because we didn't care about the fact that, P1 had X1. We only care about X2. So coming out of step 2, both caches are in the S state. And now for times 3, P1 is going to request X1. So that's going to trigger P1 to go to M. And you're right. In this case, depending on how the concurrence protocol is implemented, if you could go from M to S rather than M to I, then it technically would not be a miss. So technically it would already be present in the cache. That may be why that was confusing. Let me go back.
But it still has to read the whole line.
Sure.
It's a miss. Because it's got to read the data that P2 just wrote.
It didn't. I believe it was only a read, right?
Oh, I'm sorry.
So here in this implementation of MSI, we allow things to go from M to S. Some protocols do not. They make it go back through I first. So I'm just going to say I'm going to rethink this slide, and I'll post a correction tonight. Because I think that should not be a miss. Okay. Actually, wait. We're about out of time. So rather than going halfway through this next segment, I'm going to pick it up there on Friday. Okay. Well, have a good day.